So the key learning objectives to go over here are the 3 types of mitigation measures that we have, which are advanced or early warning measures, emergency measures, and permanent measures. So the first measure is advanced measures, something that you can do in anticipation of a breakup or jamming event. The goals of advanced measures are to increase flood protection, reduce the supply of ice available for jamming, to potentially control or influence the sequence of an ice breakup event, and to potentially increase the conveyance area for ice, or basically give the ice somewhere to go to help an ice run progress and move downstream without creating a jam. These are non-structural measures, meaning that we're not going to go out and build something on the channel to influence the ice. These are things that can typically be implemented within a short lead time of 2 weeks to 6 months. They can be inexpensive, but that's definitely not always the case. So first on the list, we'll talk about is ice motion detectors. There are a lot of different ways to do this. This one here is just an example of a tripwire system that is triggered when the ice moves. This one was built by Crow and installed on the Kennebec River in Maine. There are other options available now that we've been thinking about using, but haven't quite gotten to the deployment stage yet. But using laser systems that work either as a rangefinder, if you're familiar with like a golf or hunting rangefinder, we've prototyped a few of those and tested them out on rivers, and they do a pretty good job of monitoring ice stages, basically just detecting if there's a significant sudden change in ice cover. And also LiDAR and radar-based systems could be used as well. But the idea is to have an automated way of detecting a sudden change in the ice surface and an indication of an ice run. So it's sort of like an alarm bell going off. So a lot of the times these things happen in the middle of the night or maybe somewhere that it isn't easy to get to or observe. So the idea is to have it be an automated process and to give folks a lead time to be able to respond. Next, we have web cameras. These are getting easier and easier to deploy due to lower cost of the actual components and more broad availability of telemetry options. Oftentimes, that was like a really big constriction. You either had to, locally store information, and then that's not very good for emergency response, obviously, or use a satellite connection, which can be pretty expensive. But now that cellular networks are becoming more ubiquitous, it's increasing the ability to deploy these in more and more remote locations. So they provide really great real-time data on ice conditions and are great for retrospective as well, like going back and trying to piece together what happened, even years afterwards if you're trying to do some sort of a study. But one significant limitation is that they don't work in the dark. So that kind of cuts out half or more of your viewing window, depending on where you are. Next, we have trained observers. This is a great option if there are individuals with the interest and ability to routinely monitor ice conditions. They can be integrated into an emergency response team and can provide real-time information about ice conditions and flooding. Observers can help track conditions leading up to the ice jam season and progression of post-breakup ice. It's very difficult to site stationary equipment in the perfect location. So some of those automated methods I talked about, often the action's just right outside the frame, or you just missed whatever you're looking for. So a human on the ground that can go out and make observations and add that human element of being able to focus on the real issues, take photos, is pretty much impossible to replicate. So a municipality, an academic organization, a government agency may provide the training for individuals. And I know up in Alaska, there's a few different programs and methods that folks at different levels of experience can contribute to ice observations, and all that information is really valuable. Next, we'll get into more physical advanced measures. We have a few key approaches here that are all aimed at mechanical weakening. So basically breaking up the ice cover and encouraging it to run early and not to jam, or prevent the existence of a strong intact ice cover that could arrest an upstream ice run. So just weakening the ice, getting that hard ice broken up into smaller pieces and help it move downstream. So there's a lot of different approaches that can be used. Things like chainsaws and ice augers have been looked at. Those are pretty localized. These small scale methods can end up being pretty labor intensive and dangerous, and kind of debatable how effective they are unless there's like a very specific localized area that's causing a routine problem. Something small like that might work. Often we see larger scale solutions that are more effective, such as ice breaking ships. On the Mohawk River this year, actually, there was a new program using tugs to do some ice breaking in some slower moving water bodies within their lock system. And that seems to help significantly with a February breakup event this year in preventing an ice run from coming down that traditionally would basically be halted by this thick ice cover on a pool upstream of the dam. That ice ran through this year, so and it's been attributed to the ice breaking activities by these tugs. So in these pictures we see, I don't have a picture of that tug on here, but there's a classic ice breaking ship, Coast Guard vessel on the top left. On the top right is a hovercraft. The Canadians use these every year out on the St. Lawrence River to break up ice. They hover over it, and basically they just sort of do donuts. They spin around on the ice, and that's enough to break it up and start to help them move around. So that's pretty effective. I'm not sure exactly what the cost benefit is on that, but it's, you know, folks going out there and doing something, and it seems to be making a difference. The contraption on the bottom left is an amphibex, which seems to be used quite a bit in Canada. I haven't personally seen them here in New England, but I know that they are used quite a bit in Canada, and it's basically a floating excavator. It can get out on the ice, break it up without the obvious significant issue of a regular excavator. If it falls in the river, that's really bad. This one, since it doesn't sink, it makes it a lot easier and safer to get out there and break up ice mechanically. So these could also theoretically be used to break up an attacked ice jam as well, but that would have to be a very situationally specific activity, because that can get fairly dangerous, especially if there's built up water upstream of the jam or something like that. So in general, the idea is to break up the ice cover from the bottom, from downstream to upstream. So it doesn't make much sense to start from the upstream, because once you break up the ice, it doesn't have anywhere to go. So working on the toe and moving up, getting the ice to move, and trying to tackle those points where the jam is really either bound by the banks or grounded to the bed, and then making sure that there's somewhere for it to go. Here's another technique that's been used. It's a plane that's dropping dust. I think this is probably coal dust on the Platte River. The idea here is to cover the ice cover with some sort of material to reduce the albedo. Reducing the albedo means that the surface can therefore absorb more solar radiation and not reflect it away. As we know that snow and snow-covered ice is a pretty good reflector of energy, so we want to capture the energy and use it to raise the temperature of the ice and eventually melt it and get back to that phase change into liquid water. The radiation is energy that'll increase the ice temperature. It can also limit the ice growth and potentially melt it too. Other things like leaves and sand have been used in the past. These methods are probably effective if conditions are right, but if it snows over the materials, that's a problem, because then it's just buried. It might become re-exposed later and can still help. But that's not ideal. And then, it could take a lot of dust or a lot of leaves, depending on how big of an area you're trying to cover. So again, if it's a smaller region, these sort of smaller scale efforts might be appropriate. It can be difficult to quantify the effects of these, though, and it makes it hard to justify the equipment and the labor and the costs if you're doing this every year. And it's a little bit tough to know, how effective this is. So. I know it's been tried in some places and discontinued. It is a good option, but like I said, the conditions have to be kind of right for it to be a good option. Next, we have moving from advanced measures, we're moving into emergency measures. So these are measures that we have at our disposal once an ice jam conditions are likely to exist, or if the jam is actually forming or has already formed. So kind of the last, you're not planning in advance now. You're kind of dealing with a situation that is evolving in front of you. So the goals are similar to advanced measures. We're trying to reduce flooding, increase conveyance of the channel, potentially remove ice from the channel to destabilize the jam and improve flow conditions. So in this section, we'll cover some of these subsections of excavation, talk about blasting. Everybody wants to talk about blasting, flood fighting, and in some cases, it might make sense to do nothing. So we'll cover that one too, because that actually is a pretty common response. So with excavation, from a purely physical and hydraulic standpoint, it makes the most sense to try to break up a jam while the stage is still rising. The conditions will be most beneficial then to try and turn a jam back into an ice run. Velocities and depths will be higher. You know, the obvious consequence of that is it's definitely a dangerous time to be out there with equipment and doing anything. So that safety is a really important consideration there, and folks shouldn't put themselves or others in danger, even if, you know, theoretically it's a better time to be out there to release a jam. So advanced planning and consideration of these sort of emergency responses is key. That if that's something that an organization thinks is a good response, it needs to be well thought out, not somebody, you know, just jumping in on a piece of equipment during the middle of an ice jam forming and trying to make a difference. So the best way to take advantage of that window of opportunity is to have pre-stage equipment. In this picture here, we have a bucket dredge that can help break up an ice jam within its reach. It can be staged in a location that sees a high probability of ice jams. As an example, in the city of Montpelier, Vermont, the capital of Vermont, there's a history of ice jams at a very particular bend in the river, Cemetery Bend. So every year, the town leases a long boom excavator and parks it on a pullout, and it's, you know, they put it there every fall and then pull it out in the spring. But it's there to, you know, be available to be put into operation at pretty much a moment's notice. So that's an effective way to do kind of a hybrid advanced emergency response. And the long boom is nice because it doesn't put the workers in the line of fire. They're operating it from the bank. It's often hard to pre-stage equipment, or sometimes an event happens so rapidly that the stage rising period is over before resources can be mobilized to a particular location. That's pretty common. You know, these things happen pretty quick. Stage comes up, ice jam forms, and then it might recede a little bit. So when the stage falls, the ice will be likely harder to get moving again. In this case, we'll want to focus on destabilizing the downstream end of the jam. Potentially the jam may be static because there's stable tow. So removing or weakening that tow may release the jam. Again, safety considerations apply to all this. Like some of these things, you know, aren't the best idea from a safety perspective. But in this case, we have a bulldozer in a channel that's moving ice. This could be an excavator or something similar, working from the bottom up. The idea here is to just stabilize the jam. This can be very dangerous, of course. In some cases, the jam is essentially a dam. So it's holding back a lot of water, a lot of energy. So breaking it from the downstream end can be like breaching a dam on top of yourself. And it can release a flood wave similar to the way that a dam breaches. So equipment needs to be deployed carefully and thoughtfully to prevent initiating an ice run or flood event that damages or destroys equipment or injures or worse, kills somebody. Access is often a huge issue with this approach. Getting equipment to the right place. Often jams will form in a place that just aren't accessible by equipment, especially the tow. So here are a couple examples of excavation of jams. The top one is probably I'm not sure exactly what the hydraulic situation is there, but that might be a good example of maybe something that's not the best idea to do. I mean, the guy's operating this piece of equipment right in the channel and kind of chipping away at this jam. And if there's not a lot of water stored upstream of it, it might not be that big of a deal. But you know, if this is holding back some water, you know, might not be the best solution to be down there in the water. And then this bottom shot here might be familiar to some folks on the call. This is some excavation that was done on Willow Creek. From what I can tell, largely done from the bank, and seems to have been pretty effective at helping you know, release some of the stored water from upstream and potentially move some ice as well. Next, we'll talk about blasting. This is a question we get probably more than any other. Everybody wants to know if they can go out and blow up a jam. So the Corps doesn't do ice jam blasting. I think maybe in the past we were more involved, but it's not something that we do or really participate in. Local agencies might, or private companies might provide that service. Similar to excavation, the idea is to work from the downstream end where things are relatively ice-free. and ice can be released, and then to move upstream. And the ideal approach is to place charges underwater and before the hydrograph recedes. So that, I mean, that's pretty challenging to do logistically, to get out there and get explosives in place like while you're still at an elevated stage. So we often talk about using explosives to break up an intact jam when the stage and flow have already decreased, and that's a pretty challenging time to try to move something, depending on the scale of the jam. And so the history of ice mitigation with explosives, from my knowledge, it's a pretty mixed bag. There's some examples when a small charge placed at the right place at the toe of a jam has been effective at releasing a jam, and then there's some examples of folks using a lot of ANFO, many pounds, and not getting any results out of it. So it's not always the best option. And so I think I'm aware, or I think I remember seeing a news article in the ADN at one point where a homeowner in Canada tried to use explosives, and I believe that the effects of that were pretty minor in freeing up that jam. There's also been some experiments with the use of aerial bombing in maybe shortly after World War II on the Yukon near Galena, and the results of that were pretty mixed as well. And the obvious downside of that is that probably generated some UXO. I don't think all those bombs necessarily detonated. So that's obviously a significant downside to that method. And to be successful, there needs to be conditions where the explosive breakup will trigger an ice run, or at least significant destabilization of the forces causing a jam. So just going out into the middle of an intact jam and just setting off charges is probably not going to do much. It's just going to move around the ice within the jam. So it needs to be a really targeted operation with some folks that kind of know what they're dealing with an ice jam before just trying to blow things up. And this is obviously not a good option if the jam's in an urban area, which is often where there's a concern because of flooding. Okay. So now the next topic in emergency measures is flood fighting. So this is an approach that isn't necessarily tied to ice jam specific flooding. It's a response to any sort of flooding. We're basically accepting that there's going to be some impacts, some flooding from the jam, and that there needs to be a flood fight to prevent damages to infrastructure and homes. So the classic measures are things like placing sandbags or jersey barriers, with BizQueen or water bladders or whatever to create temporary dikes. Many municipalities will have an evacuation plan for riverine type flooding, and maybe even for ice jam flooding as well, which is a key plan to have in place if you've got specific residences that are in an ice jam flooding prone area, to have that plan in place so that if an ice jam occurs, that you can kind of look at something that's already been thought out and get folks who may be in a vulnerable area out quickly. And flood fighting can go in parallel with ice removal and other active measures to reducing flood impacts. So these aren't exclusive options, obviously. And then the last is the do nothing approach. This is viable if there's weak ice that isn't really capable of generating a jam or significant jam. Basically, if the ingredients aren't right for an ice jam, there isn't really a reason to do much. If there isn't a significant volume of ice, the ice is weak, the weather forecast is for gradual warming without a lot of rain. So if those sort of conditions exist, ice can melt out thermally, get weak, or maybe just go down or be gone when the river stages start rising in the spring. So it's important to kind of assess how severe the situation is, even if there is broken up ice on the river, if it's not causing major problems. It's important to kind of weigh that scenario with putting people at risk and equipment and stuff to try to do something if there isn't necessarily an acute flood risk. Okay, last we'll discuss permanent measures. So the goals of this are again to ultimately provide flood protection. That's kind of a paramount thing we're trying to do here. This can be accomplished by reducing the supply of ice to ice jam prone locations, typically by arresting it upstream. That's the kind of primary mode, but also through permanent measures that can help limit ice growth. That's another kind of class of permanent measures, which we'll talk about. With measures like permanent ice control structures, which we'll cover in this section, the objective is to displace the ice jam location. So we're trying to move typically the ice jam location upstream where the economic and public safety impacts from flooding are less severe, or maybe even zero if you've got an ideal case or ideal location, like an undeveloped zone upstream of an ice jam prone location in an urban area or a populated area. So we're talking about structural solutions here, actually going out and building something, permanent infrastructure and all that entails. So that involves design, permitting, construction, maintenance. These type of projects can take a long time to get into place, years, and in some cases decades. The solutions are usually only viable when there's a clear expectation of high benefits, meaning a significant reduction in flood impacts. They're generally pretty expensive options, but there are lower cost options that we'll discuss that may be appropriate for some locations. So the first one we'll talk about is ice booms. These are floating booms that are pretty common for debris control in their hydro plants. Folks have probably seen these before. Just optimized for ice control. We're trying to hold back ice and not woody debris and that sort of thing. In the past, timber booms were pretty common, but now we typically see steel or HDPE. They tend to be a little more buoyant and robust. They're most effective for combating freeze-up type jams, typically early in the season. So ice is collected upstream of the boom and can help prevent the movement of frazzle ice into downstream areas. So some of those images that Jeremy showed you where you got all this, frazzle ice that's accumulating around bridges and that sort of thing, that could all be kind of held back with a boom. The boom can also encourage the earlier formation of a continuous ice cover, which can encourage local accumulation of frazzle ice from upstream and prevent the formation of new frazzle. So you're kind of inducing an ice cover by kind of holding it there with this boom, trying to create a continuous ice cover so then frazzle that's coming down from upstream accumulates underneath it. And then because there's this lid now over the ice, if you recall some of the heat transfer stuff we talked about, frazzle ice is not going to form under that ice cover. So you're then reducing the amount of the river reach that can actually produce frazzle ice to cause problems downstream. So it can be a pretty effective means to prevent freeze-up jams. So in order for an ice boom to work, the flow velocities need to be pretty low. Somewhere around 2 feet per second is an upper threshold. Need a little bit more. Otherwise, ice can simply run over the boom, or in some cases, the forces in the cables and the anchor systems can get quite high. So there's some design procedures to consider, when going into designing a boom for a particular location. There also needs to be a suitable area upstream of the boom for the ice to accumulate. That's kind of obvious, but you gotta have a place to store all this ice that isn't going to cause some other adverse impacts. There may also be some stage rise that needs to be accounted for, so you're creating a rougher surface condition, which we'll talk about in the hydraulics of river ice later. But you're potentially going to see some stage rise in this area. And so if the site conditions are right, booms can be reliable. They can be relatively low-cost solutions. There's some annual maintenance requirements, and some of the components will experience some wear and tear over the years. But often they're removed in the spring and can be serviced, but also to allow vessel traffic and prevent woody debris accumulation and that sort of thing as well. So those can be a good option. Next, we have ice control weirs. So that's the same concept as a boom. And at least basically, the idea is to retain frazzle ice upstream of a problem area and encourage formation of a solid ice cover. These are much more significant structures than stringing out some floating booms on a cable. It's basically a low head dam. And there are some pretty significant related downsides to this, such as public safety concerns. Some of you who are familiar with dam safety issues might know that low head dams are a really significant drowning hazard due to hydraulic current that they create downstream. So that's a real serious concern. And then obviously fish passage. Depending on how it's designed, it could be a significant impediment to fish. So, they have been shown to be effective in some locations, but there are some downsides too. And the other benefit of these structures is that they tend to be decent at limiting ice run progressions as well, so that beyond just accumulating frazzle ice during the freeze-up season, they create a competent ice cover, and then an ice run coming downstream can impact that competent ice cover and maybe stop upstream. So an ice boom can serve a similar purpose, but you know, these being a little bit more robust structures, that benefit's a little more defined. So there's a lot of, or at least several good examples of effective ice control structure weirs that I've shown here in the picture. The top left is Cherryfield ice control structure in Maine, which has been in service for many decades. I think it was built in the 60s, 50s or 60s. Below that, there's a weir on Oil Creek in Pennsylvania. And the top right is in Lancaster, New Hampshire. The bottom right is a concept design of an inflatable weir that could be used in the same scenario, but to my knowledge, they haven't been used yet. They're pretty common on run-of-river hydroelectric dams, you know, on the crest of a dam, to potentially change the stage of the water going into the turbine. But it's basically a large rubber tube that can be inflated and will tip up some armor plates on the upstream face to prevent, you know, damage from impacting debris. And the benefit is you can have a weir when you need it in the winter to perform this function of capturing frazzle ice and creating an ice cover. And then in the spring, when the ice is gone, you can deflate it and then potentially store it on the bed. And that can limit a lot of the real negatives of a permanent weir. So fish passage issues, obviously, and some of the public safety issues can go away as well. So obviously there's maintenance issues to consider. It's a much more, you know, complicated type of structure, mechanical components and that sort of thing, but that is an option. And it would be interesting if somebody wanted to install one of those. We'd be really interested to work with somebody on that, because I think it is a good option. So here's an example of some ice mitigation strategies that have been employed in Oil City, Pennsylvania. We've mentioned both of these already, but it's actually a site where both a boom and a weir are used together to limit ice jam flooding. So the weir is on a frazzle-producing creek upstream of the problem area, up at the north end of the figure. The problem area is down there near the confluence of the Allegheny River and Oil Creek. And the boom's on the main stem of the Allegheny, just you know, between the numbers 131 and 132 there. Show you, yeah. So these are some aerial images here, just showing the boom in a deployed state. It's a two-span boom, and then it's stored in the spring, and I think that's a boat that's moving it through there. So it's not an impediment to navigation or, you know, folks canoeing or anything like that. So these two combined structures seem to have worked pretty well for Oil City. So when we talk about ice control structures, some people, at least, you know, out here where we've got a few of these types of structures, they often think of pier type structures. And there is an example of one here on the bottom right figure. They're primarily for displacing the location of a breakup jam. So these other measures are focused more on freeze-up jams. These are for mechanical breakup jams primarily. They basically induce an ice jam at a controlled location and hold it there, often until the ice thermally melts out in the spring. So it's just, you get a jam there and you hold it there until it melts. An important design consideration is the ability for flow to still make it through or around the jam and not cause unacceptable flooding, like overtopping, ice overtopping the flooding of the structure. There's also a few different designs that have been built, but they're all some form of piers embedded or anchored into the bed, which then transmit the forces of an ice run or jam into the foundation of the stream. So that example is from the Cazenovia Creek ice control structure that was built near Buffalo, New York. The Corps is involved in this project, Buffalo District, in cooperation with the local community. Consists of reinforced concrete piers that are socketed down into a bedrock foundation. It's a really robust and maybe even a bit conservative design. It's not going anywhere. And so extensive testing was conducted both actually here at Krell and some of our refrigerated laboratory spaces, which you can see on the bottom left figure there. The idea there was to evaluate some of the upstream stage impacts. How much is the water going to go up if you're accumulating ice here, and to look at the flow patterns, jetting, that sort of thing, and forces on the structure. The structure was built and then shown to be effective at arresting ice runs and preventing ice jams downstream. So one key thing to point out for this structure is that on the top right photo, adjacent to the structure, on the bank opposite where those houses are, the developed area, there's a low floodplain. This is an ice control structure flow bypass. This is a pretty critical element, and it provides a place for the river's flow to go when an ice jam is arrested at the ice control structure. So, you're creating the jam, catching it at these piers, but then you want the water to be able to have somewhere to go without just a significant stage rise, which could cause kind of unpredictable behavior or potential overtopping of the structure where the ice just becomes released because the stage rises so fast. So this is kind of a blow-off valve. And armoring against scour in that area turned out to be a really important design consideration. There were some modifications that had to be made to the structure because of that significant scouring. Next, we have the ice control structure on the Salmon River in Connecticut. This is similar to the Cass Creek project in that there's a row of piers perpendicular to the main channel. However, this one has a row of piers running off diagonally, which is there to extend the face of the jam and provide more flow capacity. This particular location didn't have a good area for a flow bypass. So this configuration will reduce the likely upstream stages during a jam. And this structure was evaluated at Krell as well. It's, again, a good example of a location where a flood bypass isn't necessarily available, and extending the length of the weir. That's actually a classic engineering trick that's used in spillway design on dams. For if those of you that are familiar with labyrinth spillways, so you're creating a longer weir length for the water to flow over, and therefore reducing the stages upstream and maybe not needing a bypass. So those are some examples of what I'd say are relatively big ticket items, big ticket projects. So not all communities impacted by ice jams experience enough damage to justify the cost of one of those, because this all comes down to kind of benefit cost ratio, how much you're going to pay to build something to mitigate damages. So to address this, some low cost structures have been investigated and built as well. This is an ice control structure in Hardwick, Vermont that was built with locally quarried granite blocks anchored to the bed. It's a pretty simple structure, and it's been pretty effective. It's actually been documented in some peer-reviewed papers being effective at arresting ice runs and preventing flooding in the town. It was built back in the 90s, mid-90s, I think, and it's still functional today. Actually, this photo here on the right is one I took just a couple years ago, and it still looks like it's in really good condition. So pretty simple solution, but pretty effective and also cost-effective. And here's another structure in Vermont. This is in Barre. This one was actually constructed primarily to control large woody debris that was coming downstream and jamming on these narrow bridges in an urban part of Barre City. The structure was installed, and then the following winter, it kind of inadvertently proved to be successful at arresting ice jams. The picture here, it's a pretty small jam, but if it had made it down to the bridge, which is just out of the view here, it probably would have caused some significant flooding. So kind of an inadvertent ice control structure. This one was built with H piles that were vibrated into the ground and then pile driven into weathered bedrock. The benefit of this approach is it's really low cost, just the cost of steel and some mobilization for the equipment. And then the piles can be reset relatively easily if they need to be, if they're displaced. Okay, last we have thermal discharge solutions. This is the last item on the permanent structures list. So this is permanent infrastructure installed to introduce warm water to a channel to limit ice growth or potentially to melt existing ice. So reducing ice thickness or weakening it can help keep ice runs from moving and prevent ice jams from forming. So there's a clear benefit to being able to do that. But the question is, where's that warm water going to come from? So some sources that may be available are from places like cooling ponds at industrial sites or power plants, or from wastewater treatment plants. The effluent from wastewater treatment plants is actually fairly warm, and depending on the scale of the river that you're trying to influence, might be enough additional thermal energy to add to the system to make a difference. And so that's actually what we see here. There's a long pipeline that runs from the wastewater treatment plant in Montpelier, Vermont, to that problem bend I was talking about, Cemetery Bend. It's weakened the ice at the bend, and again, it's a little bit difficult to quantify how effective this is, but it's pretty clear just observationally that it's weakening the ice and creating a zone where not a whole lot of ice forms. So the impact area is not huge, but it's definitely helping. So some other areas, some other sources of warm water include groundwater from deep water in a reservoir or lake, for example. If you've got a really deep body of water, there might be, you know, a pretty significant reservoir of 4-degree water, which can, even though that sounds cold, that's warmer than zero. So that can actually be useful in trying to increase the temperature of the river or stream. And this can be an effective and inexpensive option if there is a source of warm water available. So in summary, mitigation measures are most effective if there's plenty of lead time, that some thought has gone into planning ahead of time. Emergency measures are a last resort, but they are, you know, the most common type of response that we have to ice jams. Pre-staging materials can help make these efforts more effective, and having some sort of monitoring system in place to be aware that ice run and ice jam conditions exist, detecting them when they start can make a big difference. So the key thing is to have a plan. Permanent measures can be a good option, but require good cost-benefit ratios. And so there are some cost-effective ice control structure technologies that are available, and they can be suitable depending on the specific location and circumstances, of course. So with that, I'll take any questions.
Hey, Chandler, I think we need to move on to the next presenter just to try and stay on schedule, but